Here are some proofs by the building blocks themselves, even though I have showed this over and over, but I guess it didn't stick, so here it is. We have a quarter-regular tetrahedron. This is a Fuller's regular tetrahedron, quarter-regular tetrahedron, 6A modules. Now we know he defines this edge as 2, which is of course wrong. This edge is the diagonal is here, 2 times square root of 2. Now, yeah, you can say edge, whatever you want to assign, at least that's what Fuller's think. Well, no, it's incorrect. Because I can fold this one up, like that, and I make a partial cube already. Everything is cube based in here. We derive all the modules from a cube. And now we see that the edges of our quarter-regular tetrahedron are changing. Now, the edge of the quarter-regular tetrahedron is cube body diagonal, square root of 2. Then the other edge is this. I mean, it's square root of 2, this is square root of 3, that's a cube body diagonal, and then this is the cube's edge. So those are the correct edges because we modeled that. I know synergetics cannot model, it's a very limiting system to model with, but that doesn't mean it's correct. Fuller is absolutely, completely incorrect. Now here we have a mite. This is a mite in Fuller's case divided into 3 modules. They are coming left and right. Well, in my case it's 2 modules coming left and right. And we see that this edge is square root of 2. This is a cube body diagonal. And this is edge 2. That's here. 1 and 2. And if I fold it like together like this, which is very clever, we have a quarter-irregular octahedron, which is basically 1/3 of a cube. 3 of these makes a complete cube. So we know and we can define our edges very accurately. Now here we have a oblate octahedron. This oblate octahedron has an inner octahedron in it. Now in Fuller's case they're saying that the octahedron is 4 times the size of a coupler. Well, no, that's only when you're using a 2-frequency octahedron and you measure it to a 1-frequency coupler. Then the relations is like Fuller says 4:1. But since this is 2-frequency and this is 1-frequency, apparently Fuller don't know what is he talking about, and anybody who follows his modeling. Because we have these in the same magnitude. Octahedron is 1-frequency and a coupler is 1-frequency. Their relationship is 2:1, coupler being twice the size of the regular octahedron. Now here is a 1/8 coupler. I want to show this. This is going to be coming from a 1/8 quarter. This is a 1/8 module. This is a irregular, half irregular octahedron, but this is 1/8 of the coupler. And this is the same thing. I want to show this. This is a solid kite and a quarter and a 1/8 octahedron. They are in the same magnitude. And I want to show here, this is a synergetics, quarter regular tetrahedron, 6 modules, and 2 mites. 3 and 3, also 6 modules. So it's 12 modules. Now here, that's 2-frequency, 1-frequency. It must be obvious to anybody. This is a 1/8 octahedron, 2-frequency octahedron of this one. This is a 1/8 of it. And it also contains 12 modules, just like the synergetic solid kite. It's made of quarter-regular tetrahedron on the bottom, and then B modules, 6 B modules, which are here on the top. So now we put them together like that, and we make the same thing like we make it in here. And this is now 1/8 building block of the coupler. So is this. So we see that the relationship, when you don't mixing up the frequency like Fuller does, the relationship comes obvious even with synergetics blocks, that the relationship of the coupler to an octahedron is 1 to 2. In other words, coupler is twice as big than an octahedron. So we're demonstrating the same relationship, not 1 to 2 and not 1 to 4. Now here are the rhombic dodecahedron. This is our rhombic dodecahedron, and we both share it in our modules, and we see that the diagonal of the long diagonal is this cube body diagonal, 2 times square root of 2. This is the edge of the cube, that's here. That's the edge of the cube. And this is the square root of 3. This is a cube body diagonal. So that's what defines the coupler. So, so 12 half couplers making this rhombic dodecahedron. We have the same couplers, we have the same rhombic dodecahedron. We cannot have different dimensions when we can model this. Now Fuller arrived at his square root of 2 edge by a total incorrect maneuver. This is how he done it. We see this is a cube of edge 2. This is what we both use. Even the Fuller mathematically uses this, tries to convert it with the constants into a rational cube, go from 2.828427125 cube to volume 3 cube. So he uses these constants to achieve that. But this is how he done his edge. He made this one triangle, which we see that it's 1/4 of this square. This square is common to both of us. And see, so he put a label here, 1 and 1 and square root of 2. This is the isosceles triangle to him, and it's a 1/4 of this square. But since the diagonal of this square stops here, does not go all the way through, it means there is an interval in here. And that interval is, where is all? That interval is here. He has 24 modules in a regular TET, and the interval is here, even though Kirby uses philosophy and some very comical relations. Of course, via modeling, we see exactly what's going on. So when a square is drawn, we have to finish this diagonal. There is an interval. And there is 24 modules in here. And these 24 modules, of course, are equivalent to 3A modules. That way we know that this is a 2-frequency regular tetrahedron.